Hello, and welcome back to tonight's story. Let every sound out there slowly fade into the distance. Tonight, we will not step into an ancient kingdom, nor follow the footsteps of a king or a lost civilization. We will go much farther than that, so far that there are no cities left, no humans, no trees, no living creature of any kind that could call Earth its home. Before us is a young planet, desolate, wild, and violent. The sky is not blue as it is today. The ocean, if it has already formed, is still strange and dark. There is no birdsong in the wind, no sound of insects beneath the grass, no breath warming the morning air. There is only hot stone, endless rain, lightning, volcanoes, meteorites, ancient waters, and the vastness of time passing slowly by. And yet, within that world that seemed entirely lifeless, something so small it was almost impossible to see began to happen. One molecule lasted longer than the others. One reaction repeated itself one more time. A thin membrane held a few particles of matter inside. And from those silent movements, life may have begun to take its very first steps. Tonight, we will follow one of the oldest questions of every living being that has ever existed. How did life begin on Earth? And where, if we can call it that? Did the first living organism emerge from the deepest darkness of time? Imagine standing in a place very far away, not far in distance, but far in time, farther than every city ever built, farther than the pyramids, the ancient temples, the dinosaur bones buried deep in stone, farther even than the first forests that ever spread green across the land. You are standing before Earth when this planet was still very young, very strange, and when no living creature had yet called it home. There is no birdsong in the air, no rustling of leaves, no insects, no fish beneath the water, no roots gripping the soil, no footprint pressed into the mud. If there is wind, it carries no scent of grass, no fragrance of flowers, no warmth from living bodies. If there are waves, they only strike against empty stone. If there is rain, each drop falls upon a world that has never known the sound of breathing. Earth at that time did not resemble the gentle blue planet we see in photographs taken from space. It was a world still in the making, still carrying within itself the heat of its birth. The rocks were still young. The surface was still unstable. The first lands, if they had already risen above the water, were not covered in green, had no soft soil, no fields, no forests. They were dark, rugged masses of stone, worn down in silence by rain, heat, and impact. The sky above was not the familiar sky we know. It did not yet have the clear blue color of an oxygen-rich atmosphere. There was no layer of air like the one today, gently embracing the ground with quiet stability. The early atmosphere may have been thick with water vapor, carbon dioxide, nitrogen, and many other gases released from the planet's interior through volcanoes. That air was not meant for human lungs. If a human being had appeared there by some miracle, they could not have breathed, could not have walked for long, could not have survived in a world not yet prepared for life as we know it. And yet, for that very reason, the scene carried an ancient beauty, a beauty that needed no witness. In the darkness of deep time, Earth was not quiet in any gentle sense. It thundered with processes larger than any human story. Volcanoes opened their mouths in the night, releasing heat, gases, and molten rock onto the surface. Red streams of lava crawled across black stone, then slowly cooled and hardened into new layers of crust. The ground could crack open, sink, rise again, then be covered once more by hot material from below. The young planet was like a vast, unstable body, still learning how to hold its own shape. High above, the sky may have often been torn open by lightning. No tree trembled beneath those flashes. No animal eyes widened in fear. Only blue-white electricity flared over a lifeless world, then vanished, leaving darkness and thunder rolling through the young atmosphere. Rain may have fallen for lengths of time impossible to imagine, as water vapor in the atmosphere cooled and condensed. Those first rains did not fall onto grass, did not flow through forests, did not rest on flower petals. They fell onto hot stone, evaporated, then fell again, repeating in a cycle that stretched across spans of time human memory could never hold. Gradually, as the planet cooled, water began to remain longer on the surface. Low regions may have become lakes, then seas, then oceans. No one knows exactly how that scene unfolded from moment to moment, but we can imagine an Earth shifting from fire to water, from a burning, red-hot surface to dark expanses reflecting a sky heavy with gases and clouds. The first ocean was not the calm blue ocean of coral, fish, and seaweed. It was an ancient body of water, deep and empty, with no sound of swimming, no flash of fish scales, no drifting clouds of tiny organisms carried by the current. Its waves only struck stone. Its currents only touched minerals. It had water, but it did not yet have life. Stay within that image for a little longer, a nameless shore of rock beneath a sky with no wings crossing it. Before you lies a vast ocean, but its surface bears none of the familiar colors of life. There is no algae to tint the water, no plankton glimmering in the bright layer near the surface. No living thing dies and sinks to the bottom to become part of a food chain. That ocean may have slowly grown salty as water dissolved minerals from rock. It may have been warm in some places, cold in others, violent beneath storms and silent through long stretches of darkness. But no matter how vast it was, it remained an ocean without biological memory. This is difficult to imagine, because in the world we know today, there is almost nowhere truly empty of life. In a handful of soil, there are countless microorganisms. In a drop of water that seems perfectly clear, there may be living beings too small for the naked eye to see. On our skin, inside our intestines, at the bottom of the sea, within cold ice, near hot springs, life always finds a way to cling on. And so, when we think of Earth before life, we are not merely imagining a world with fewer living things. We are imagining an almost absolute silence, a depth of emptiness so profound that everything familiar to us had not yet come into existence. There was no spring, because no flowers had yet bloomed. There was no autumn, because no leaves had yet fallen. There was no morning in the way we understand it, because no birdsong awakened the forest. The sun still rose, light still spread across stone and water, but no living thing received that light in order to grow. Night still fell, darkness still covered the ocean, but no eyes needed to close in sleep. Time did not pass through heartbeats, lifespans, birth, and death. It passed through the cooling of rock, the gathering of water, the collision of minerals, and the slow transformation of the atmosphere and the planet's surface. Sometimes, from space, other objects still came rushing in. Meteorites and fragments left over from the formation of the solar system may have fallen onto Earth's surface, creating violent impacts. Each large collision could vaporize rock, carve out enormous craters, and throw dust and heat into the atmosphere. But we should not imagine early Earth only as an endless hell. Over time, between those upheavals, there were also more stable intervals, regions where water could exist, mineral surfaces that could meet gas, heat, and light. Those relatively stable moments mattered, because if life was to begin, it needed more than violent energy. It needed a place where reactions could repeat, accumulate, and be tested across time. Here, the story begins to grow quieter, but also deeper. A planet without life does not mean a planet without activity. On the contrary, everything is in motion. Water flows across stone. Gases escape from volcanoes. Minerals dissolve into the ocean. Sunlight touches the surface of the water. Lightning supplies powerful bursts of energy in the atmosphere. Heat from the planet's interior pushes streams of material upward. Gravity pulls water into low places. Tides. If the moon had already settled into its orbit around Earth, may have made the water rise and fall along ancient rocky shores. None of these processes is alive. None has purpose. None has consciousness. But together, they create a world full of interactions. And within that world, the basic elements were already present. Carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and many other elements existed in rock, water, gas, and minerals. They had not yet formed living bodies. They did not yet belong to cells, blood, bone, leaves, or bacteria, but they were the rough alphabet of every living thing that would come later. Before there can be a story, there must be letters. Before there can be a living being capable of maintaining itself, there must be materials for nature to arrange, break apart, and arrange again in countless different ways. What is strange is that, looking back from the present, we know that our own bodies are also made from those ordinary elements. There is no separate mystical substance that divides life from the universe. The carbon in cells, the water in blood, the minerals in bone, the energy in every breath, all belong to the same physical world. But on the young Earth, the boundary between lifeless matter and life had not yet been crossed. All the ingredients may have been there, but no organism had yet used them. All the energy may have been flowing across the planet, but no body had yet held on to it in order to live. That is what makes this story both scientific and almost mysterious. Not mysterious because we need to invent anything beyond the evidence, but because what happened in nature is already profound enough. From a world without consciousness, without breath, without memory, living beings eventually appeared, beings capable of growing, copying themselves, adapting, evolving, looking back at the sky, and wondering where they came from. But at this point in the story, all of that still lies ahead. Earth does not yet know that it will have forests. The ocean does not yet know that one day it will be filled with fish, algae, coral, and whales. The sky does not yet know that oxygen will slowly change the color and life of the planet. Everything is still waiting in the long silence of the beginning. If we placed an imaginary hand upon an ancient rock in that world, we would feel no pulse, only lingering heat, the dampness of rain, the salt of water splashed up from the ocean, and the roughness of minerals. Yet it may have been on surfaces like these that water and rock met across millions of years. Tiny cracks held droplets of water. Ancient shorelines left mineral films behind each time the water withdrew. Shallow ponds evaporated beneath the sun, then filled again with rain. Deep regions beneath the ocean received heat from the planet's interior. Each place like that was a kind of stage, not a stage for living creatures, but for chemistry being tested again and again. Still, we must remember that nature does not experiment like humans in a laboratory. It has no plan. It does not know it is moving toward life. Most reactions likely led to nothing lasting. Molecules formed and then broke apart. Structures appeared and dissolved. Too much heat could destroy them. Too much water could dilute them. Ultraviolet light, impacts, environmental instability. All of these could erase fragile steps that had only just begun to form. But Earth had one thing that human beings find almost impossible to fully feel: time. Not a few years, a few centuries, or a few thousand years, but millions and hundreds of millions of years of repeated possibilities. Across that span of time, the planet did not need to hurry. A rocky shore could be struck by waves through countless days no one counted. A pool of water could dry and fill again through long cycles. A crack beneath the seafloor could maintain heat and minerals long enough for countless reactions to occur. What seems to us like a nearly impossible accident could, within the deep time of Earth, become a vast chain of opportunities, not because life was guaranteed to appear, but because the young planet had enough matter, enough energy, and enough different environments for even very rare events to have a chance to be tried. Imagine an evening on ancient Earth. The sun sinks behind a horizon of black stone. No birds fly home to their nests. No animals call to one another in the forest. No fire is kindled by human hands. There is only the darkening sky, clouds heavy with water vapor, distant flashes of lightning, the smell of volcanic gases, and the sound of waves striking rock. The ocean before you is so vast it seems as though it could already contain the entire future, yet it remains empty. Beneath the surface, minerals drift, currents move, temperatures shift, small reactions occur and disappear. No story is being told there, but the conditions for the story are being prepared. Perhaps the most important thing when entering the origin of life is to accept slowness. We often want to find a clear moment, a shining boundary, a single instant when before it nothing lived, and after it the first living organism appeared. But nature rarely works along such sharp lines. Life may not have begun like a bell ringing, but like a very faint dawn after a long night. At first, only a little light at the horizon, then a little more, then slowly, by the time we notice, the darkness is no longer quite what it was. So, in the opening of this journey, We do not need to rush in search of the name of the first living organism. We do not yet need to imagine what shape it had, where it lived, what it ate, or how it reproduced. Before there could be an organism, there had to be a world complex enough for an organism to become possible. And young Earth, with all its violence, loneliness, and instability, was slowly becoming that world. It was not gentle, but it had water. It was not completely stable, but it had moments of calm. It was not alive, but it was full of energy. It had no memory yet, but it had time. Looking from the present, we can sense in that silence a very deep kind of suspense. Everything familiar to us is still waiting ahead, like a secret not yet opened. One day, the ocean will no longer be empty. One day, stone will preserve the faint traces of tiny living beings. One day, the atmosphere will change. One day, on the same planet that once had no sound of breathing, there will be damp forests, giant reptiles, flocks of birds, cities glowing through the night, and us as well, sitting quietly in the dark, listening to the story of our own distant beginning. But for now, let everything remain at that first point, a young Earth turning slowly in space, a young sun shining down on stone and water, a moon, if we look upward, perhaps appearing larger and nearer in the ancient sky, rain falling onto a planet that has no scent of earth after rain, because living soil does not yet exist, waves striking shores no one has named, clouds passing overhead, casting no shadows on any forest, and beneath all those movements, a small possibility is being quietly prepared. Earth does not yet know how to breathe, but it already has water to hold things, stone to react, heat to drive change, lightning to stir the air, minerals to build with, and time to wait in that vast emptiness. Nothing guarantees that life will appear. No promise is written in the rock. There is only a young, restless planet, opening countless chemical doors in the darkness. And from that world without a single breath, the longest story on Earth is about to begin. The young Earth was not merely an empty planet. It was a planet in motion, boiling, breathing through volcanoes, being washed by rain, stirred by lightning and ancient waters. If, in the previous part, we stood before a world without life, now let us move closer to the places where life may have been prepared, not by a sudden miracle, not by a complete living creature emerging from the darkness, but by small reactions, repeating again and again through stone, water, gas, heat, and time. Imagine an afternoon in the unimaginably distant past, when Earth's sky was still heavy with water vapor and volcanic gases. Clouds hung low, thick, and dark, as though the entire sky were bending close to the young ocean below. No tree stood to catch the wind, no bird crossed the horizon. Only sudden bolts of lightning tore through the air, flashing for a single moment before vanishing, leaving thunder rolling across the dark water. Each bolt lasted only an instant, but it carried immense energy. In a world filled with gases, water vapor, and simple molecules, that energy may have broken old bonds and pushed atoms into new combinations. This is one of the most famous images people imagine when thinking about the origin of life. An early atmosphere, a lightning strike, an ocean or shallow pond below, and from those collisions, the first organic compounds beginning to form in the imagination. It is as though the sky were writing the first strokes onto the page of life. But the scientific story must be told more gently and carefully. Lightning did not create living organisms. It did not turn water and gas into a cell. What it may have done, under certain conditions, was provide energy for simple molecules to combine into more complex organic molecules, the small building blocks that life might later need. In 1953, two scientists, Stanley Miller and Harold Urey, carried out a famous experiment to test that idea. They created a closed system, allowed water to evaporate, mixed it with several gases thought to possibly resemble the early environment, and then sent electrical sparks through the mixture like artificial lightning. After some time, amino acids appeared in the solution, molecules that are important in modern life. That experiment did not prove that life began exactly that way, nor did it say that Earth's ancient atmosphere was certainly identical to the model in the laboratory. But it opened a great door in the scientific imagination. Perhaps the building blocks of life did not need to be made by living things that already existed. They could form from lifeless matter if the environment had enough energy and the right conditions. Picture that scene, not inside a modern laboratory, but on the surface of the young Earth. A shallow pool lies among dark rocks. The rain has just stopped. Steam still rises from the warm ground. Above, clouds gather again, and lightning strikes in the distance, lighting the surface of the water for a moment. Within that water are simple molecules, minerals dissolved from stone, gases from volcanoes, heat from the sun, and wet-dry cycles stretching across countless days no one could count. Each time the water evaporates, the substances inside may become more concentrated. Each time the rain returns, they dissolve again, move, collide, and arrange themselves in new ways. Most of it leads nowhere, but nature does not need every reaction to succeed. It only needs enough opportunities for a few chemical pathways to become more stable, more complex, and more capable of continuing. Shallow ponds, small lakes, rocky shores, and tidal zones therefore become very intriguing stages. There, water does not remain forever in one state. It can fill after rain, withdraw under sunlight, and leave behind thin layers containing minerals and organic compounds. Such cycles may help molecules meet more closely. Instead of being diluted in the vast ocean, sometimes a small pool may be more useful than an immense sea, because in a smaller space, everything is held closer together. Just as a crowded room makes strangers more likely to bump into one another, a drying pool may give molecules more chances to react. But Earth did not only have pools beneath a sky of lightning. If we walk along that ancient shoreline, past dark sheets of rock and warm vapors rising from the ground, we would see a planet filled with different environments. In some places, water touched sunlight. In others, newly cooled volcanic rock still held heat. In some places, minerals dissolved by rain flowed into small lakes. In others, tides left streaks of salt and mineral residue on stone. Each place was like a different variation of the same vast experiment. An experiment with no designer, no goal, no observer, but one that stretched across the deep time of the planet. At times, strange visitors also fell from the sky. Meteorites, cosmic dust, and fragments left over from the formation of the solar system may have carried organic compounds to Earth. This does not mean that life necessarily came from outer space. It only suggests that the ingredients of life may have had more sources than we once imagined. Some may have formed on Earth. Some may have been delivered by objects wandering through space within those cold stones. Certain organic molecules may have been created far away, in environments unlike Earth, and then fallen into the ocean, onto rocky shores, or into the lakes of the young planet. Imagine a small meteorite streaking across the black sky, burning bright, breaking apart, then falling into a shallow body of water. Around it, no one is astonished. No tribe looks upward. No story is told beside a fire about a falling star. There is only water splashing up, rock cooling, minerals dissolving, molecules being released into a new environment. Once again, most of it may lead nowhere. But for a planet that already has water, heat, rock, gas, and energy, every new source of raw material makes the chemical picture richer. Yet if we remain only on the surface, the story is still incomplete beneath the ancient ocean where sunlight could not reach. Another stage may have existed, darker, deeper, and far stranger. Let the imagination leave the rocky shore, drift out to sea, and sink downward. The water above slowly grows darker. The thunder in the sky disappears. The light fades, then vanishes completely. Pressure rises. Temperature changes. And on the sea floor, within thick darkness, cracks in Earth's crust may be releasing hot water, minerals, and streams of chemicals from the planet's interior. Hydrothermal vents are unlike any seen on land. There, seawater seeps down through cracks, comes into contact with hot rock deep below, then rises again carrying minerals, metals, and chemical compounds. In the darkness without sunlight, columns of hot water may rise like black smoke or white smoke, depending on their mineral composition. Around them are stone, pressure, heat, and powerful chemical differences. If Earth's surface was where lightning fell from the sky, then the deep sea floor was where energy rose from the heart of the planet. What made those vents special was not only heat, it was difference. The difference between hot water from Earth's interior and the colder seawater around it. Between an environment rich in certain chemicals and another environment poorer in them. Between small rocky chambers and the vast ocean beyond, modern life, no matter how complex, still depends on differences like these. A cell does not live by stillness. It lives by energy flowing through it, by the difference between inside and outside, between one substance and another, between places where there is more and places where there is less. That is why deep-sea vents become such compelling candidates in the story of life's origin, because they naturally create continuous flows of energy and matter. Look more closely at those rock structures on the seafloor. They are not only giant chimneys. Inside and around them may have been countless tiny holes, cracks, and chambers, like a maze made of minerals. Those chambers could keep molecules close together, protect them from being diluted by the ocean, and at the same time allow chemical streams to pass through. On the surface, a shallow pool may concentrate molecules through sunlight and evaporation. Beneath the sea, tiny openings in rock may isolate and concentrate molecules in a different way. There is no light, no lightning, but there is heat, minerals, pressure, and a steady chemical flow. In that darkness, the story becomes very quiet. There is no dazzling spectacle like a bolt of lightning striking the sea. No sky, no clouds, no horizon, only black water, hot stone, and invisible streams of chemicals mixing together. But sometimes, the darkest places hold the most enduring processes. A lightning bolt is powerful but brief. A hydrothermal vent may maintain a flow of energy for a much longer time. If life began in such an environment, it may not have begun with light from above, but with warmth from Earth's interior and the patience of rocky chambers beneath the deep sea. Of course, no one can go back to see whether that truly happened. The hypotheses about shallow ponds, lightning, shorelines, meteorites, or hydrothermal vents are all ways science tries to reconstruct a story that time has almost erased. Each model has strengths and difficulties. Shallow ponds may help concentrate molecules, but they may dry too much or be damaged by ultraviolet light. The deep ocean is stable and rich in chemical energy, but too much water may dilute reactions, and high temperatures may break apart some fragile molecules. Meteorites may deliver organic ingredients, but ingredients alone are not enough to create life. No stage is absolutely perfect. Perhaps the origin of life did not belong to a single place, but was the result of many environments contributing together, many chemical pathways opening on a young and restless planet. What matters in this part of the story is not choosing a winner in the debate too quickly. What matters is understanding that the early Earth was not poor or barren. It was not a meaningless ball of rock waiting for life to appear from nothing. It was a planet with water to dissolve, rock to catalyze, gases to react, lightning to provide energy, volcanoes to release material, meteorites to add ingredients, the sun to warm the surface, and Earth's interior to sustain deep currents of heat. Before life existed, this planet was already a vast network of chemical possibilities. Return once more to the shallow shore. The rain has stopped. The clouds part for a moment, letting the young sunlight fall onto wet stone. In small pools, water rests between cracks in the rock. Perhaps simple organic compounds are present there. Perhaps some came from the atmosphere after storms of lightning. Perhaps some came from volcanic rock, some from meteorites, some from reactions in the water. As the sunlight rises, the water slowly evaporates. The substances inside become more concentrated. When rain returns, they are stirred again, separated, joined, and carried elsewhere. Across a single day, nothing remarkable may happen. Across a year, perhaps still nothing, but across millions of years, such cycles become a chemical breathing of the planet. Then let that image merge with the scene beneath the deep sea. Above, lightning strikes across the sky. In the middle, the ocean rolls through ancient darkness. Below, hot water bursts from the rock, carrying minerals and streams of energy that need no light. The young Earth seems to have many hearts beating at once, one heart in the sky, with electricity and rain, one on the surface, with shallow water and warm stone, one beneath the seafloor, with heat and chemicals from the planet's interior. None of those hearts is alive in the biological sense, but all of them are creating movement, and movement is necessary for matter to have the chance to become complex. In those environments, simple organic molecules may appear and vanish. A few molecules may be more stable. A few reactions may occur more easily in the presence of minerals. The surface of a certain kind of rock may hold molecules just long enough for them to meet. A drying pool may draw them closer together. A crack beneath the deep sea may place them within a continuous stream of chemicals. But here, we still do not yet have life. We are only standing at the edge of pre-life, where the bricks may form, where energy may push them into more complex structures, where nature begins to have more materials with which to try the next steps. And it is precisely this incompleteness that makes the story so compelling. If life is a city, this is not yet the moment when the city lights have turned on. This is when stone is being quarried, wood is being gathered, roads are being traced in silence. But no house has yet been completed. If life is a piece of music, this is not yet the melody. This is when the first notes are being created, scattered, out of rhythm, not yet knowing where they will lead. If life is a flame, this is when the world is still gathering wood, drying branches, making sparks, but no fire has truly begun to burn. Perhaps for millions of years, Earth tried countless paths and erased them. A pool dried too quickly. A stream of hot water destroyed molecules that had only just formed. A large meteorite disrupted an entire sea region. A promising reaction stopped because it lacked the needed ingredients. Those failures left no memory. They did not fossilize. They did not write their names in stone, but they were a natural part of the process before any system became stable enough to continue. There may have been countless systems that were not stable enough to survive. Before one path was preserved, there may have been countless dead ends swallowed by time. So when we look at the early Earth, we should not search for one simple moment, not only a lightning bolt, not only a pond, not only a vent beneath the sea. Perhaps the true story lies in the combination of many things. On the surface, light, lightning, and wet-dry cycles may have created certain molecules. Beneath the deep sea, heat and minerals may have created other reactions. Meteorites may have supplied additional ingredients. Volcanoes may have continually released gases and new material into the atmosphere and oceans. The young planet did not have a single laboratory. It was an entire planet of laboratories. In that view, Earth is no longer a dead, silent landscape. It is a place being prepared, though it does not know what it is preparing for. Every rain falling onto hot stone, every bolt of lightning crossing the atmosphere, every meteorite fragment dissolving in water, every stream of hot water rising from the sea floor, every tidal cycle along a rocky shore. All of them are small touches upon a great story that has not yet found its main character. Life has not yet appeared, but the stage has gained many layers. There is not only stone and water, but reactions, ingredients, flows of energy, places of concentration, and spans of time long enough for nature to keep trying. Imagine now that we stand at the boundary between two worlds. Behind us is Earth entirely without life. Only stone, water, and gas. Ahead, far away, is the world of cells, inheritance, evolution, forests, animals, and humans. Between those two worlds lies this part of the story, quiet, without a clear shape, but profoundly important. This is the twilight zone between ordinary chemistry and biological possibility, a place where matter is not yet alive, but has begun to contain enough complexity to one day move closer to life. Night falls on the surface of the young planet. The lightning grows distant. A shallow pool lies still among the rocks. Offshore, waves continue to move through the darkness. Beneath the deep sea, the vents still release their silent heat, like lamps without light beneath the ocean floor. No living creature witnesses it. No memory is preserved. But if we could listen with imagination, we might hear the very slow rhythm of the material world, a rhythm moving from chaos toward possibility, from scattered ingredients toward more complex structures, from absolute emptiness toward a threshold never crossed before. Earth is still not alive, but it is no longer only cooled stone and dark water. It now has places where energy meets ingredients. It has chemical currents passing through minerals. It has cycles of gathering and dispersing, breaking and combining, failing and trying again. And in those natural laboratories, from the lightning-filled sky to the deep sea floor, the young planet is quietly moving closer to the next great question. How can a molecule do more than simply form and disappear, and begin to preserve a trace of itself? How can chemistry, amid countless blind collisions, one day carry information? That answer no longer belongs to the spectacle of lightning or vents. It lies at the next threshold of the story, where matter may begin to enter the strangest thing of all, memory. Imagine a world where everything happens and then vanishes. A bolt of lightning flashes across the ancient sky, blazing for a single moment before dissolving into the darkness. A drop of rain falls onto hot stone, evaporates, and leaves no trace behind. A molecule forms in a shallow pool, drifts away, collides, breaks apart, and returns to smaller fragments within the vast flow of the ocean. The young Earth, at that time, did not lack motion. It had energy, water, stone, gases, minerals, and places where chemical reactions could occur. But motion alone was not life. A storm also moves. Lava also flows. Ocean waves also repeat themselves across millions of years. What was still missing was something very strange, very fragile, and very profound: the ability to preserve a trace of itself. This is where the story enters a realm harder to see than anything that came before. We are no longer standing before red glowing volcanoes, no longer watching lightning strike the water, no longer simply observing the dark vents deep beneath the sea. We are bending down into a smaller, quieter layer, where molecules drift through water, cling to mineral surfaces, join together and break apart again, trying countless shapes with no one to guide them. In that world, almost everything is temporary. A structure appears, then disappears. A chemical chain lasts a little longer, then is destroyed by heat, light, water, or another reaction. Nature is patient enough to let countless failures pass without needing to remember them. But life, if it was to begin, could not be only reactions appearing and dissolving forever. It needed some way for the past to touch the future. Some system had to exist long enough to influence what happened next. Some structure had to be capable of making something nearly like itself again, or at least helping similar structures appear more often. This was not memory in the human sense of remembering a face, a voice, or a distant rainy night. It was memory in its most primitive form. Information preserved in the shape of matter. Think of the modern living body. Every cell within us contains genetic information, stored in DNA, like an unimaginably small library arranged with astonishing order. From that library, the cell knows how to create proteins, control reactions, repair itself, divide, and maintain life. But if we look closely, modern life resembles a completed city with roads, factories, libraries, electrical systems, workers, and its own rules. The question of life's origin is far more difficult. Because in the beginning, that entire city could not yet have existed, we cannot simply say that DNA stores information. Proteins do the work, cells use energy, and then consider everything explained. The real problem is this: before such a complete system existed, what played the first role? DNA is very good at storing information, but in modern life, DNA usually needs proteins and many complex machines to be copied, read, and repaired. Proteins are very good at performing chemical work, but the information needed to make proteins is usually stored in DNA. The question becomes a quiet circle. If DNA needs proteins, and proteins need DNA, then which came first? It is here that many scientists turn toward a strange and important intermediary: RNA. RNA can be understood, gently, as a close relative of DNA, but more flexible and more fragile. In modern cells, RNA performs many different tasks. It can carry information from DNA to the place where proteins are made. It can participate in the process of reading the genetic code. And what makes RNA especially compelling in the story of life's origin is that some RNA molecules can not only carry information, but also catalyze chemical reactions. In other words, in certain cases, RNA can be both like a small note and like a tiny hand that helps work happen faster. From this came a famous idea, the RNA world hypothesis. According to this hypothesis, before modern life clearly divided the roles between DNA and proteins, there may have been a very ancient stage in which RNA-like molecules played a much more central role. They may have stored information. They may have participated in reactions. They may have created versions nearly like themselves, or at least supported the process of copying in some way. We must say this carefully. No one can claim with certainty that the entire origin of life unfolded exactly as a complete RNA world. This is a strong and influential hypothesis. But many questions remain unresolved. Even so, it gives us a beautiful framework for imagining the transition from ordinary chemistry to chemistry with information. Imagine a small body of water on the early Earth. We do not need to call it the cradle of life. We only need to see it as a place where matter had a chance to stay closer together. Water rises after a long rain, then recedes beneath the sunlight. Minerals from the rocks dissolve into the water. Some simple organic molecules are present in the solution, perhaps created by reactions in the atmosphere, by geological environments, or added by fragments of material falling from space. On a damp rock surface, a few molecules cling, some separate, some join together into short chains. Most of those chains are unstable. They disappear quickly, like lines drawn in sand and erased by waves. But imagine that, among countless attempts, one chain lasts a little longer, not because it wants to exist, not because it knows anything, only because its shape, its bonds, and the circumstances around it make it harder to break apart. Then another chain, by chance, helps a certain reaction happen more easily. Another may cause nearby molecular fragments to arrange themselves in an order nearly like its own. There is no consciousness, no plan, but there is difference. And when there is a difference between structures that last briefly and structures that last longer, between structures that do nothing to their environment and structures that make near copies of themselves appear more often, nature begins to have something to select from. That is a threshold extremely difficult to see, yet profoundly important. Before that threshold, chemistry is only chemistry. Reactions happen according to physical and chemical conditions, then end. After that threshold, something new can appear: history. If a certain kind of molecule increases the chance that molecules like it will appear, then the past is no longer completely erased. It leaves a trace in the future. A more stable chain may become more common. A more accurately copied chain may preserve information better. A chain that creates new variants may open more possibilities, and among those variants, some may continue better than others. This is the very earliest shadow of evolution, before organisms existed in the familiar sense. But we should not imagine everything unfolding neatly. As it might in a textbook, the first molecules, if they existed, were certainly not perfect. Copying could have made many errors. Chains may have been short. Systems may have collapsed easily. A small change in temperature, acidity, salt concentration, light, or minerals could have broken apart a chemical path that had just begun to form. Nature may have created countless forms of almost life and then lost them. Structures stable only for a few hours, a few days, or a few wet-dry cycles. Systems that seemed promising but could not continue when the environment changed. Reactions that once came close to something greater, then vanished without leaving any trace in stone. That is why the origin of life does not resemble an invention with a clear date. It is more like a dawn stretching across deep time in the first darkness. No one could point to a single spot and say, here, this exact moment, matter became life. There may have been many intermediate steps, many temporary forms of organization, many systems still too simple to be called organisms, yet already more complex than ordinary chemistry. There may have been lines of molecules competing in silence, with no eyes to see, no mouths to eat, no bodies to move, yet with the ability to maintain some kind of information across time. And in that way, matter began to have a very strange form of memory, not memory in the mind, but memory in the order of bonds. Let this image slow down. A molecule does not know it exists. It does not fear disappearing. It does not hope to be copied. It is not moving toward humans, trees, or any future at all. But if its structure causes nearby fragments to arrange themselves in a way that creates a similar chain, then it has done something completely different from a stone lying still or a drop of water evaporating. It has caused the shape of the past to be repeated in the future, only a little, imperfectly, without purpose, but enough for the story to change direction. In the modern world, we often think of information as something invisible, a sentence written in a book, a photograph in a phone, a memory in the mind. but at the level of life. Information must always have a physical body. It lies in the sequence of molecules. It depends on shape, bonds, energy, and environment on the early Earth. If a molecular chain could hold information, that information did not lie on paper, nor in sound, but in the way chemical units were joined together. Each different sequence was like a very short sentence written in a molecular alphabet. Most of those sentences were meaningless or too fragile. But some may have done something. Some may have influenced reactions. Some may have prolonged their own chemical existence. From this perspective, the memory of matter is not merely a poetic idea added to the story. It is a way of understanding why information matters so deeply. A planet may contain countless organic compounds, but if no system can preserve and pass on its own order, everything may remain only a stream of scattered reactions. An environment may produce amino acids, sugars, organic bases, and many other complex molecules. But life needs more than a storehouse of ingredients. It needs a mechanism to choose a few possibilities among countless possibilities, and then cause those possibilities to be tried again, revised, expanded, and made to compete with one another. Mineral surfaces may have played an important role in that stage. A rock surface is not merely a motionless floor beneath water. At a tiny scale, it can be a place where molecules cling, are held close together, are arranged in a certain direction, or are partly protected from being swept away by water. Small cracks, mineral layers, and constantly changing wet-dry regions may have helped molecular chains form more easily than if they drifted freely in the vast ocean. Of course, we are still speaking with scientific caution. May have. Possibly. Some models suggest. But within this evidence-grounded imagination, stone and water are no longer a lifeless backdrop. They become the rough hands of the planet, holding, pressing, drying, wetting, warming, and stirring molecules across time. In another place, beneath the deep seafloor, chemical streams may have flowed through small rocky chambers. Somewhere else, a shallow pool may have slowly dried under the sun, drawing molecules closer together. We do not need to decide immediately which place is correct. What matters is that in many different environments, Earth was creating the same kind of opportunity, the opportunity for molecules not merely to appear individually, but to become chains, not merely to exist for a moment, but to last a little longer, not merely to be carried away, but to leave an influence on the next reaction. That is the difference between a sound that rings out and fades, and a melody beginning to find a repeating rhythm. If an RNA world existed, it certainly did not resemble a living world in the familiar sense. There were no complete cells swimming through the water, no predators, no plants absorbing sunlight, no bodies clearly distinguishing themselves from the rest of the environment. It would have been a world of fragile molecules, short chains, unstable reactions, flawed copies, structures appearing and dissolving. But within that clumsiness, something very great may have begun. The difference between what continues and what disappears, we can imagine millions of years passing like a long night with no one awake. In that night, the oceans rise and fall. Rain comes and goes. Rock cracks open. Minerals dissolve into water. Ultraviolet light touches the surface. Deep currents of heat continue to surge upward. Molecules form, break apart, join again, deform, and break again. But somewhere, within countless tiny motions, a structure may have done something a little more unusual. It preserved an order. It helped that order repeat. It allowed errors to occur, and within those errors, variants appeared. Not every variant was better. Most may have been worse, weaker, more short-lived. But some may have been more stable, faster, better suited to the surrounding environment. This is when we begin to see the shadow of natural selection before true organisms existed. No guiding will is needed. No final goal is needed. There only need to be different systems, the ability to create similar versions, and differences in the ability to continue. Systems that maintain themselves better leave more traces. Systems that collapse disappear over time. The molecular world may gradually lean toward structures that hold information better, catalyze more effectively, and cooperate more successfully with their environment. From the outside, everything remains silent, but within that silence, a kind of history has begun. This makes the story of life's origin feel closer to us than we might think. Deep down, we are still beings of information. Every cell in the body is holding an ancient text, copied, edited, and passed down through countless generations. But that text did not appear complete from the beginning. Before the long books of modern DNA, there may have been very short, very fragile lines, written by delicate molecules in ancient water, before memory in the brain, before history in spoken stories, before names and language. Matter may have learned how to record something simpler than all of them, make something nearly like this again. And perhaps that very simplicity was one of nature's greatest steps. A stone may exist for millions of years, but it does not copy its shape into a later generation. A cloud may carry a beautiful form, but it dissolves without passing on the formula of itself. A bolt of lightning may be more powerful than any tiny molecule, but it vanishes the moment it appears. Yet, a fragile molecular chain, if it can help create another chain nearly like itself, has entered an entirely different game. No matter how weak it is, the game of continuation. From here, the question of life is no longer only where did organic molecules come from? The question becomes, how did some molecules begin to carry information? And how did that information avoid being lost immediately? This is a region science is still exploring. Through experiments, models, geochemistry, molecular biology, and many competing hypotheses. No simple answer is enough to close the mystery. But that incompleteness is exactly what makes the journey deeper. We are looking through a narrow doorway between lifeless matter and life, where every step is so small it is almost impossible to see. Yet its consequences stretch all the way to every breath today. Imagine one final time in this chapter, an ancient surface of water beneath a dark sky. No living creature swims through it. No eyes look upward. No complete cell has certainly appeared in that scene. There are only molecules, rock surfaces, flows of energy, and repeating cycles. But in one very small corner of the world, there may have been an order that did not vanish completely, a chemical shape preserved for a little longer, a sequence repeated imperfectly. An error became a variant. A variant lasted longer. No one called it memory. No one called it evolution. No one called it a beginning. But time does not need names. Earth still has no forests, no animals, no sound of breathing, but matter, somewhere in the darkness of water and stone, may have begun to do something it had never done before, preserve a part of itself and pass it into the next moment. And when matter began to remember, even in the most fragile way, the story of life took a very long step toward dawn. Ancient Earth was not vast only in its dark oceans, its empty rocky shores, or the storms that covered the sky. It was also vast in places so small the human eye could never recognize them. A pool of water resting quietly between cracks in stone could be an entire world. Within it, molecules drifted past one another, touched, separated, then met again in ways no one controlled. A few fragile chains may have held some kind of information. A few reactions may have repeated one more time before disappearing. But no matter how important that was, one great problem remained. If everything simply drifted freely in water, how could a tiny system hold itself together? In the vast ocean, molecules were easily diluted. A chain that had just formed could be swept away by the current. A reaction that had only begun could immediately lack the next ingredient it needed. A structure that had become just a little more stable could be separated from the very things that helped it continue. If life was to move beyond scattered chemistry, it needed more than a molecule with memory. It needed a place where important things could be kept close together. It needed a small space, a private region, a fragile boundary that said, "This is inside, and that is outside." It may sound simple, but a boundary is one of the deepest ideas in the story of life. Without a boundary, there is no body. Without an inside, there is no way to maintain a private order amid the chaos of the outside world. A stone has a surface, but inside it is not a living system exchanging, repairing, transforming, and continuing. A drop of water has a shape for a moment, but it can easily merge with another stream of water. Life needed a boundary softer than stone, more flexible than a mineral shell, yet strong enough to hold reactions within and open enough to let matter and energy pass through. Here, the story brings us to a very special kind of molecule. Molecules with one part that likes water and another part that avoids water. In simple terms, they are like non-living beings with two temperaments. One end prefers to stay near water, while the other turns away from it. When such molecules are present in a watery environment, they can arrange themselves into very natural shapes. The water-avoiding part turns inward, away from contact with water. The water-loving part faces outward, and from that simple arrangement, thin membranes, tiny sacs, and molecular bubbles can form. A membrane thinner than anything the naked eye could see closed into a small pouch drifting through ancient water. It was not yet a modern living cell. It did not yet have complete DNA refined enzymes, or a complex machinery like the bacteria of today. But it had one very important thing: an inside. There. A few molecules could be held for longer. A few reactions could happen closer together, and fragile chains could avoid being diluted immediately. Before membranes, everything could easily dissolve into the wide current of water. A useful molecule appeared, then drifted away. A reaction had barely taken place before its product was carried off. But when enclosed inside a tiny pouch, however primitive. The world began to have its first chemical room, soft, fragile, yet enough to hold a little order amid the chaos. Such primitive sacs may have formed in shallow ponds, near warm coastlines, or inside rocky chambers where water, heat, and minerals pass through. They were not miracles, but natural results of the properties of molecules capable of arranging themselves into membranes. What mattered was not exactly where they appeared, but that nature could create simple boundaries before life itself truly emerged. When that little pouch held a few molecular chains, a few organic compounds, and a little temporary order inside it, inside began to mean something. It was no longer exactly the same as outside. If the membrane retained useful components, reactions could continue for longer. If the pouch was more durable and exchanged better with its surroundings, it had a greater chance of lasting than pouches that were too leaky, too weak, or unable to hold anything significant. That may have been a very quiet step forward in natural selection. Before. The difference lay in individual molecules. But when molecules were gathered inside a small pouch, nature began to select an entire chemical package. It was no longer only which chain was more stable, but which combination could hold itself together longer, react better, and continue for more time. The first membranes were certainly not as perfect as modern cell membranes. They may have been leaky, fragile, and constantly changing. But that very imperfection may have been useful if the membrane was too sealed. Raw materials could not enter. If it was too open, everything inside would drift away. A primitive membrane needed a delicate balance, closed enough to preserve an inside, but open enough to exchange with the world beyond it. Over time, those tiny sacs may have grown when they encountered more membrane material, then been stretched and divided by water currents, stones, or changes in temperature. This was not reproduction in the full sense, but if some of the molecules inside were divided into new sacs, then we are already seeing a very faint shadow of multiplication. The membrane mattered not only because it enclosed, it created a difference between inside and outside, and that difference was the foundation for energy to be used. Modern life still depends on such gradients, differences in concentration, electrical charge, and chemistry across the cell membrane. On the early Earth, everything was far more primitive. But as soon as there were two sides, nature had a new foundation for energy flow to become more directed. For that reason, life may have needed a home before it could become a body. That home had no stone walls or wooden doors. It was only a thin membrane trembling in ancient water. But inside it, molecules were no longer entirely lost. They were closer together, influenced one another more, and had a chance to become a system instead of scattered fragments. Information and boundary began to need each other. Molecular information could help maintain an inner environment. A membrane could protect that information from being lost. When these two things met, a new possibility appeared. A small space could carry its own chemical history from that thin membrane. Life took another very slow, but very deep, step toward the first cell. Here, we are standing very near the boundary between pre-life and life, but we should not cross it too quickly. A protocell, or pre-cell, is not a complete living cell. It is a model, an idea of intermediate systems that may have existed before organisms as we understand them today. It had a membrane, could contain molecules, could exchange with the environment, and could grow and divide under certain conditions. But it did not necessarily have stable heredity, complete metabolism, or the long-term self-maintaining ability of modern cells. That incompleteness is precisely what makes it suitable for the story of life's origin. Because nature usually does not leap straight from nothing to a perfect machine. Let us imagine a world filled with imperfect protocells. They drifted in water, clung to stone, gathered in small hollows, broke apart under currents, grew when they encountered more membrane molecules, and split in two when stretched. Inside some sacs, reactions stopped very quickly. Inside others, reactions lasted longer. Some membranes were too weak, some too sealed, some too leaky, but somewhere, among countless experiments, there may have been tiny sacs that held a slightly better balance. Not better in any absolute sense, but better than the sacs around them in the same environment. Selection at this stage, if it existed, must have been very crude and ruthless in nature's silent way. Systems that could not hold themselves together dissolved. Systems that lasted longer had more chances to change. Systems that divided while still carrying important components had more descendants. Though that word is still too modern for this period. Over time, small differences could accumulate. A more stable membrane, a more useful reaction, a more effective way of exchanging with the environment, a tighter link between the information inside and the enclosing layer outside. All of it could create a slow path toward the first cell. The birth of inside was not only a chemical event, it also suggests a very deep image of the nature of life itself. Every living being, from the smallest bacterium to the human body, exists by keeping a private world that does not completely dissolve into the outside. Our bodies have skin. Every cell has a membrane. Organs have their own boundaries. Even the mind, in a certain sense, is an inner space where memory, feeling, and thought are held amid the endless flow of the world. But before all of that, before the brain, the heart, or any complex body, there may once have been a very thin molecular membrane. It did not know what it was protecting. It had no awareness of separateness, yet that fragile layer may have created the first boundary between inside and outside, between one portion of matter held together and the rest of the vast ocean. From that boundary, the original meaning of life began to appear. Return to that tiny bubble in ancient water. It did not know it was one. It had no name, no purpose, no sensation. But compared with the water beyond it, it had a difference. Inside, it was a separate collection, a separate condition, a separate possibility. If it broke, that difference disappeared. If it lasted, that difference continued a little longer. And in an unimaginably vast universe, where most matter simply followed forces and reactions, the fact that a small space could hold its own order, even for a moment, was something astonishing. Perhaps millions, even billions of tiny sacs like that formed and dissolved without leaving any trace. There is no fossil that shows us the first membrane, no layer of rock records the moment an inside first appeared. What we have is chemistry, modern biology, experiments, models, and imagination held within the limits of evidence. But sometimes, the most important things in history leave no clear image behind. They leave only consequences. And the consequence of the first boundary is the entire living world that came after. From a thin membrane, a new possibility opened. Molecules could stay closer together. Information could be preserved longer. Energy could pass through a boundary instead of spreading evenly through the environment. A system could be different from the rest of the world. From that difference, after many more steps, true cells, then populations, then long evolution could eventually become possible. But in this chapter, we only need to listen to that very small moment, the moment the world was no longer completely uniform. The moment there was a trembling inside between water and stone. Night falls again on ancient Earth, in a shallow pool. Thin membranes shimmer where no one can see them, deep beneath the sea. Rocky chambers still hold streams of chemicals moving through darkness. On the surface, rain may fall, then stop, leaving thin films of water in cracks between stones. In countless tiny places like these, boundaries form and break apart, like unshaped breaths of a planet not yet alive. No living creature awakens in that night. No heartbeat sounds. No body moves with awareness of its own existence. But somewhere, matter may have learned something new, not merely to remember through sequence, but to keep that memory inside a small room of its own. A thin membrane had created the difference between inside and outside. A molecular pouch had transformed ancient water into a space capable of holding history. And from that fragile separateness, the story of life took one more step, quietly but irreversibly, toward the day when a chemical system would not only exist for a moment, but begin to maintain itself as something alive. After the first thin membranes created a space of inside, the story of life began to take on a clearer shape. It was no longer only molecules drifting freely through ancient water, no longer only reactions that came and went like brief echoes in the darkness. Now, somewhere on the young Earth, there may have been tiny systems capable of holding on to a little order, a little information, a little difference between themselves and the world around them. They did not yet resemble any living creature we know today, but they had moved closer to what we would later call a cell. And then, from countless fragile experiments, through lost pathways, through lines of life that left no descendants, through structures that once existed and then vanished completely, one branch finally continued, not because it had been chosen in advance, not because it was powerful in the way we usually imagine strength. Perhaps it was simply a little more durable, held information a little better, used energy a little more efficiently, and passed on more of what made it itself. From that incredibly distant branch, all life that exists today, from bacteria in deep mud to ancient trees, from fungi in the forest to whales in the sea, from a bird outside the window to our own bodies, can be traced back to one common point. That common point is called Lusa, the last universal common ancestor of all living organisms on Earth. But we must say this slowly, because this is where misunderstanding can easily begin. Luca was not the first living organism. Luca was not the first moment when matter became life. Before Luca, there may have been many other forms of life or pre-life, many other lines of early cells, many other microbial worlds that passed through existence and disappeared without leaving descendants. Luca was only the last common ancestor of the lineages that survived long enough to still be present in every living being today. Think of an ancient forest. If we look upward, we see countless branches and leaves interwoven, each branch reaching in a different direction, each leaf with its own shape, each trunk carrying its own scars from wind, rain, and time. But if we follow all those branches downward, deep into the shadow of the trunk and roots, we see that they once separated from shared points. The tree of life is like that, only wider and deeper than imagination can easily hold. Humans, animals, plants, fungi, bacteria, and archaea do not stand apart as separate stories at the deepest level. They are very distant branches of a shared history. What makes Luca special is not that we found its fossil lying intact in stone. There is no piece of bone, no footprint, no clear shape we can point to and say, "This is Luca." It was too small, too ancient, and perhaps too much like a simple cell to leave behind an easily recognizable trace. But modern living bodies preserve another kind of evidence, quieter and deeper. That evidence lies in the very way life operates. All living beings today, no matter how different they are, share very ancient foundations. They use a genetic code to turn information into life. They use molecules to make proteins. They use energy according to principles that are deeply related to one another. The cell of a bacterium, a leaf, a fish, and a human being are so different that they seem to belong to separate worlds. Yet, at the molecular level, they still speak different dialects of the same ancient language. It is this strange unity that leads scientists to believe that all life still existing today shares one very distant ancestor. Luca may not have been a single individual living alone in an ancient ocean. That image is too much like a story with a central character, too much like the way humans like to name a starting point. Reality may have been far more complicated. Luca may have been a population, an ancient community of cells, an early lineage of organisms exchanging genes, living within a microbial ecosystem in which most other branches eventually went extinct. When we say LUCA, we are not necessarily speaking of one single organism, but of a deep node in the tree of life, the place to which every living lineage today can be traced back. The world of Luca, if we try to imagine it, would not have looked dazzling. There were no forests, no animals, no eyes, no calls, no hunting or fleeing as in the biological worlds that came later. If Luca lived near mineral-rich regions, near hot rock, in an environment without oxygen, then its world may have been very dark, very simple, and utterly foreign to human senses. It may have been a world of water, stone, heat, gases, minerals, and cells so small no one could have seen them with the naked eye. But within that smallness, something vast was preserved, a way of living capable of continuing. Luca may have lived on an Earth still very different from the one we know today. The atmosphere was not yet rich in oxygen as it is now. The ocean did not yet have fish or large algae. The land was not yet covered by plants. If life existed, it was mainly microbial life, quiet, tiny, spread through environments that the modern human eye could easily overlook. Yet it was in that world without grand scenery, that the fundamental mechanisms of life became defined deeply enough to continue all the way to the present. This makes Luca both distant and near. Distant because it belongs to a time almost impossible to imagine, billions of years before all human history, before dinosaurs, before animals, even before the complex cells from which our own bodies are built. But near, because every living being today still carries its trace. Not in conscious memory, not in legend, not in a story passed from generation to generation, but in the chemistry of cells, in the way information is read, in the way energy is used, in principles so familiar to life that we often fail to notice how ancient they are. No living creature remembers Luca. No species preserves its image. There is no call, no instinct, no dream that can return to that place. But in a way deeper than memory, all living beings carry it within them, a bacterium dividing in a drop of water, a young plant opening its leaves in the morning mist, a bird sleeping quietly on a branch, a child breathing evenly in the night. All of them are continuing a current that began long before any brain existed to understand it. Look, in imagination, into a cell of your own body. It is so small that you cannot see it without a microscope, yet inside it is an entire living city. Information is read, proteins are made, energy is transformed. The cell membrane holds the boundary. Molecules enter, leave, interact, repair, and replace. That cell belongs to a modern human being, a complex organism with thought, memory, and language. But many of its basic principles have roots so deep that they reach far beyond anything humans have ever called history. In Luca, those principles may have been simpler, rougher, less stable, but they were enough to create a common foundation. Perhaps Luca had a form of genetic code. Perhaps it had ribosomes or an ancient machine for making proteins. Perhaps it used ATP or similar energy molecules to sustain living activity. Perhaps it lived without oxygen, because free oxygen was not yet a familiar part of the world at that time. All of this must be said with caution, because Luca left no direct portrait behind, but from what all living beings today share. We can glimpse the shadow of an ancient living system, one far less simple than we may once have imagined. What is astonishing is that Luca did not appear at the end of an easy story. Before it lay a dense darkness of time, where chemistry, protocells, early systems, and the first lines of life may have competed, cooperated, disappeared, and changed continuously. Many paths may have opened and then closed. Many early forms of life may once have existed, but left no descendants in the world today. What we see now is not the entire history of life, but only the part of that history that survived. This is like standing before a great river and trying to guess every stream that once flowed into it. We see the present current, see it continuing to move, see it nourishing fields and cities along its banks. But countless small branches in the past have dried up. Countless underground streams have changed direction. Countless turnings have vanished beneath soil and stone. Luca is the deepest point we can trace back from the river of life still flowing today. But beneath and before it, there may still have been an entire source region hidden by time. So, calling Luca the common ancestor does not mean that everything before it was unimportant. On the contrary, every step before it helped make it possible. molecules that could hold information, thin membranes that created an inside, flows of energy passing across boundaries, reactions that could repeat, systems that could grow, divide, maintain themselves, and pass on part of their own structure. Luca stood upon the foundation of all those things. It was not a miracle separated from history, but a connecting point in a very long chain of transformation. Perhaps the world around Luca was not empty either, if Luca is the ancestor of all life today. That does not mean it was the only organism of its time. Around it, there may have been other lineages of life, other ancient relatives, other microbial communities also harvesting energy, exchanging matter, competing for environments, and perhaps even exchanging genetic material. But across billions of years, only part of that picture continued into the present. The branches that left no descendants disappeared from the tree of life we can observe. They are like voices that once sounded in a very ancient room, but no sound from them reaches us today. From that perspective, every living organism is a piece of evidence: an ant crawling across the ground, a moss plant clinging to damp stone, a drop of pond water filled with microorganisms, a person sitting quietly in the night to listen to this story. All are descendants of what did not disappear. Every living body is the result of an almost unimaginable chain of continuation through harsh environments, ancient climate changes, meteorites, volcanoes, changing seas, ice ages, extinctions, and renewals. If any link in that chain had been completely broken, we would not be here. There is a deep humility in this thought. Humans often tell history through grand things: empires, wars, inventions, cities, names carved into stone. But the true history, far longer than all of that, begins with things that had no names, tiny cells that left no monuments, microorganisms that did not know they were living at the beginning of a planet that would have a future, metabolic pathways with no story, yet they kept life going. Before any king existed, before any language existed, before any eyes saw the dawn and called it beautiful, there were tiny living systems quietly maintaining their flame. Luca, therefore, is not a character whose portrait we can draw clearly. It is like a deep shadow at the root of the tree of life. We cannot see its face, but we can see that every branch above connects back to it. We cannot hear its voice, but we can see its molecular language echoing in every cell. We do not know exactly which crack in the rock it lived in, which ocean, which warm region, but we know that a line of life beginning from it was not extinguished. And that line, after billions of years, became the vivid and complex living world around us. When thinking of that common ancestor, the distance between humans and bacteria may begin to feel different. On the surface, we are vastly different. Humans have brains, memories, language, art, fear, hope, and questions about our own origins. A bacterium is only a tiny cell, living by rules far simpler than ours. But at a deeper level, both are different ways life continues to hold itself together. Both use information. Both need energy. Both rely on fragile boundaries so they do not dissolve into the surrounding world. Both stand upon the same ancient root. And if we look even more broadly, all living beings become strangely familiar. A leaf on a tree is not only a green object outside the window, it is a very distant relative. A fungus growing in damp soil the invisible bacteria on stone, seaweed drifting in water, all carry within them the shared traces of a past no species can remember. Life on Earth is not a collection of separate stories. It is one single story that has branched countless times. Night falls over the ancient planet in our imagination. There is no familiar sound, no forest for the wind to pass through, no large creature moving beneath the moonlight. Only water, stone, heat, darkness, and tiny cells living in their first ways. Perhaps among them, one ancient cellular lineage carried the traits that every later living being would inherit. It did not know it was an ancestor. It did not know that one day humans would name it Luca. It did not know there would be forests, flowers, dinosaurs, birds, whales, or cities glowing with light. It simply continued. And sometimes that may be the greatest thing life has ever done, not understanding itself, not reaching toward some distant goal, simply continuing in the darkness through one more day, one more cycle, one more division, one more difference passed onward. From that silent continuation, the entire tree of life grew. From an ancestor no living thing remembers. Every living thing today still carries Earth's deepest memory, not in words, but in the very way it lives. After everything that had unfolded in the darkness of water, stone, and chemistry, the story of life began to leave its first traces. But those traces were not what humans usually expect. There was no skeleton lying intact in stone, no footprint pressed into mud, no shell, no tooth, no leaf, no body clear enough for us to look at and immediately recognize life once existed here, in that faraway age. If life had already existed, it was smaller than anything the naked eye could see. It was soft, fragile, without bones, without hard shells, without any majestic form that could fossilize easily. And so, when scientists search for the first life, they are not searching for ancient animals. They are searching for the shadows of microorganisms in stone. It is a very quiet kind of search. People walk across dry lands, ancient cliffs, layers of sediment pressed, heated, and deformed across billions of years. In their hands is not a dinosaur skeleton, but only a piece of gray, brown, or black rock, silent-looking like any other stone. Yet within that silence may lie a question greater than all empires and all civilizations. Here, within this layer of rock, is there still any trace of the first living things that once clung to Earth? Ancient rocks do not tell stories in words. They tell them through layers, through shapes, through chemical composition, through tiny ratios between elements. To read them, humans must learn another language, slower and stricter than the language of texts. A layer of sediment may reveal whether an environment was once a shallow sea or a hot spring. A domed structure may suggest microbial mats that once trapped mud and sand over time. A carbon signal may hint that a biological process once took place. But every sign must be examined carefully, because rock can also deceive. Lifeless geology can sometimes create shapes that resemble life. Heat and pressure can distort evidence. Time can erase the clearest parts, leaving only faint fragments that force humans to debate. In that investigation, stromatolites are among the most important images. They are not individual organisms, but layered structures that may form when microbial mats trap and hold sediment. While minerals gradually settle and harden them, If we look at an ancient stromatolite, we may see nothing that resembles a living body. It may only be a low, rounded, quietly layered mass of stone. But what matters is how it was built, layer upon layer. Like a slow memory of microbial communities that once lived on the surface. Picture a shallow body of water on a very ancient earth. No fish swim through it. No large seaweed sways. No seashells rest beneath the sand. There is only faint light falling onto the water, stone beneath it, fine sediment, and thin layers of microorganisms clinging to the surface. They are so small that no one standing there could see them with the naked eye. Yet over time, they hold onto tiny grains of matter. One layer rests upon another. Minerals seep in and harden them. The soft living things disappear, but the structures they helped create remain. Billions of years later, humans bend over a stone and try to read within it the voice of a world almost completely lost. What is strange is that those traces are both powerful and fragile. Powerful, because they can survive across spans of time impossible to imagine. Fragile, because their meaning is not always clear. Was a structure in the rock created by microorganisms, or only by minerals arranging themselves? Is a carbon ratio a trace of life, or could it have a non-biological origin? Is a shape resembling microbial mats truly biological, or the product of rock being compressed and transformed? The farther we go into the past, the harder the question becomes. The older the evidence, the more easily it can be destroyed, distorted, or misunderstood. So, when we hear about traces of life 3.5 billion years old, 3.7 billion years old, or even older, we need to hold two feelings at once: wonder and caution. Wonder, because if those signs are correct, life appeared very early in Earth's history, while the planet was still young and still full of upheaval. Caution, because science does not live on delight before a beautiful story. It needs testing, criticism, measurement, comparison, and the acceptance that some things still cannot be stated with certainty. The story of the first life is not a clear, straight line. It is like a map with many corners burned away, leaving only a few lines for us to follow. In Western Australia, in the ancient rocks of the Pilbara, scientists have found traces considered very important in the search for early life. The rock layers there once belonged to another Earth, where oceans, hot springs, mineral surfaces, and microorganisms may have coexisted in shallow environments. When standing before those strata, people are not only looking at a dry landscape of the present, they are looking at the remains of a world compressed into stone, a world where life, if it existed, did not roar, did not run, did not leave bones, but only thin layers, small traces, and repeating structures. In Greenland, within heavily transformed ancient rocks, certain signals have also been proposed as traces of very early life. Such claims drew the attention of the world because they could push the history of life even deeper into the past, but precisely because they are so ancient. Those pieces of evidence are also debated. The rocks have passed through pressure, temperature, deformation, time, and geological processes that may have changed their original shapes. A sign that appears biological may need many layers of verification before it is widely accepted. And in that caution, science does not make the story less mysterious. It makes the story more truthful, because the most moving thing is not that we have an easy answer. The moving thing is that humans still try to read traces almost erased by time. A geologist holds a small piece of rock in their hand, looks at the thin layers inside it, measures its composition, compares it with modern environments, examines every lifeless possibility before daring to speak of life. It is a very patient way of listening, not listening to a voice, but listening to the silence of stone, where the first organisms, if they were ever there, remain only as ghosts of a living activity long gone. We call them ghosts not because they were not real, but because they no longer have bodies. Those microorganisms, if they once lived, vanished so long ago that not a single cell remains intact. They left no faces, no movements, no behavior we can easily imagine the way we imagine an animal. They left only the mark of how they interacted with the environment, clinging to surfaces, holding sediment, changing the chemistry around them, using energy, growing, multiplying, and then dying. Their lives may have been so small that each individual almost had no story of its own, yet their communities may have been durable enough to write a few faint lines into stone. Look at a stromatolite as if looking at a very ancient city, but a city of microorganisms. There are no streets, no rooftops, no human voices, only thin layers of life settling upon one another across time. Each layer was once a surface where tiny living things met water, light, or minerals. Each layer was covered, then another formed, across enough time. That microbial community did not merely live on stone, it helped create stone. It turned living activity into geological architecture. And that is one of the strangest things about life. Even when it is so small as to be invisible, it can still leave a shape in the physical world. But not every sign of ancient life is a shape. Some lie in chemistry. Modern life tends to use certain forms of carbon differently from many lifeless processes. And so, when scientists find unusual carbon ratios in very ancient rocks, they may ask, could this be a trace of biological activity? That question is fascinating, but it is also difficult. Carbon can be rearranged. Rock can be heated. Non-living processes can also create some misleading signals. Therefore, no single sign is enough to tell the entire story. Many pieces must point toward the same answer: a suitable environment, a suitable shape, suitable chemistry, a reliable age for the rock, and the ability to rule out non-biological explanations. The more we think about this, the more we see how humble the first life must have been. It did not enter history with a loud sound. It left no monuments. It did not immediately dominate the planet. Perhaps for hundreds of millions of years, life was only a thin layer on stone, a microbial film in shallow water, a community in mineral cracks, a small world hidden between mud, water, and faint light. If someone had stood on that ancient shore, they might not have realized Earth was alive. The ocean would still have looked empty. The rocks would still have been silent. The sky would still have held no birds. But on a smaller level, the planet was no longer the same. Once life appeared, even if only as microorganisms, Earth began to have a new kind of activity. Before that, rock was altered by wind, water, heat, and chemistry. After that, there was another force, living beings, small but persistent. They could change sediment surfaces, affect minerals, exchange matter with the environment, and, across long spans of time, leave signals that rock would preserve. Life was no longer merely something living on the planet. It began to become part of the way the planet was written onward. Perhaps this is why ancient rocks can be so deeply moving. We often think of rock as a symbol of stillness and life as movement. But in the oldest rocks containing biological traces, those two things meet. What once lived becomes stone. What seems silent preserves the memory of living activity. An ancient stromatolite is no longer a soft microbial mat. It has become a mineral structure. But precisely because it became stone, part of the story survived long enough to reach us. Imagine a scientist standing before a cliff in a dry, hot land. Wind blows past, dust clings to their shoes. Around them, there is no ancient ocean anymore, no fresh microbial mats covering the water's surface. There is only rock, but when a hand touches that surface, the distance of billions of years suddenly becomes very thin within a single object. Present and past overlap. A world without eyes, without speech, without memory in the human sense, is sending us a small signal. Here. Perhaps life once clung. Those signals are never completely easy to read. Sometimes a discovery is announced with great excitement, and then other groups examine it again and offer a more cautious explanation. Sometimes a structure once considered biological is later suspected to be geological. Sometimes a chemical sign is very promising, but still not enough to become a firm conclusion. This is not a weakness of science, but the way science protects itself from stories that are too beautiful. When searching for the origin of life, the desire to believe in an answer must always go together with the discipline of doubt. And that very doubt helps us respect the past more. Ancient Earth does not owe us a clear story. It did not preserve every piece of evidence so that humans later could understand it easily. Many ancient rock layers have been recycled by plate tectonics, melted, buried, transformed, or eroded away. Most of the planet's earliest record has been lost. What remains is only a few torn pages from an enormous book. We are not allowed to write carelessly into the blank spaces. We can only read carefully what still remains, and then acknowledge where the evidence is stronger, where it is hypothesis, and where debate still continues. In the storytelling voice of ancient rock, there is a patience humans easily forget. A sediment layer does not form in haste. A stromatolite does not grow like a castle built in a day. A chemical signal is not preserved to impress anyone. Everything accumulates in the slow rhythm of Earth. Microorganisms live, die, are covered over, replaced by minerals, buried deep, compressed, and then wait billions of years before a species curious enough appears to cut stone. Look through microscopes, measure isotopes, and ask, is this the trace of the most ancient ancestors? Here, the story of life's origin touches something very close to us. Humans are also creatures of memory. We preserve memory through the brain, through writing, through images, through stories told at night. But Earth preserves memory in another way. It preserves it in stone, in sediment layers, in minerals, in structures that seem lifeless. When we read ancient rocks, we are not only studying biology, We are asking what this planet remembers about the moment it began to live. Perhaps the first microorganisms never knew what they were beginning. They did not know that one day life would create oxygen, create forests, create animals, create eyes, ears, sleep, and questions. They simply lived in their environment, took in energy, maintained themselves, multiplied when they could, and left behind very small traces. But history is often built from things like that, not from grand intention, but from persistent continuation. A thin layer living one more day, a community holding one more layer of sediment, a chemical signal buried instead of erased. Little by little, life began to have a record of its own. Looking back from the present, we know those traces are only the smallest visible part of an immense past. Life may have appeared before the clearest evidence we possess. Many early forms of life may have left nothing behind. The first microbial communities may have lived in environments whose rocks were later completely destroyed. What we call the oldest traces are not necessarily the first life. They are only the oldest witnesses lucky enough to survive in the geological record. This is very important because it helps us avoid confusing the first evidence we find with the first moment life truly appeared. So ancient rocks do not answer everything. They only open a narrow doorway. Through that doorway, we see an earth that had begun to live in ways very small, very quiet, and very different from the world of animals and plants that came later. We see microbial communities that may have built layers on stone. We see the chemistry of life perhaps touching sediment. We see that before the planet had green forests or an oxygen-rich sky. It already held faint biological signs like the first strokes of ink on a very old page. Night falls in our imagination over an ancient sea. Shallow water covers rocky surfaces. Microbial mats, if they are there, lie still beneath the dim water, so thin they almost have no shape. Grain after grain of sediment settles. Small layer after small layer is held in place. No one sees it. No one names it. No sound announces that history is being written. But in that silence, life begins to leave its mark on matter far harder than itself. Billions of years later, when human hands lift a piece of rock beneath modern light, that story has not been completely lost. It has only become difficult to read. The ghosts of the first life do not appear as clear images. They appear as rippling layers in stone, as carbon signals, as repeating structures, as possibilities carefully weighed between biology and geology. And perhaps it is precisely their faintness that makes them more profound. Because our origin is not carved in large letters across the ground. It is written very small, very slowly, in ancient rocks that have been silent almost since the dawn of the living planet. At first, life did not resemble a conquest. It did not step onto earth with roars, with claws, with towering tree trunks, or with schools of creatures swimming across the oceans. It began so small it was almost impossible to see, so fragile that even a slight change in heat, water, minerals, or environment could have erased an entire line of progress. If there was a first cell stable enough to continue. It did not know what it was opening. It did not know that one day this planet would have forests, flowers, animals, eyes looking up at the sky, and humans sitting in the night asking where life began. It only did the most fundamental thing life can do: hold itself together, use energy, pass on information, and continue. In that ancient world, even a simple cell was already a miracle. It did not have the radiant beauty of a rainforest, the power of a great animal, or the complexity of the human body, but inside its tiny membrane, a private order had been preserved amid the vast ocean. Information was copied, reactions were sustained, energy entered, was transformed, and helped that system keep from dissolving back into chaos. From the outside, all of it may have been only an invisible speck in ancient water. But at a deeper level, Earth now had something entirely new. Matter did not merely exist. It had begun to maintain itself through time. Those earliest forms of life may have lived on a planet very different from our world. There was no oxygen-rich sky, no soil covered with roots, no grass, no forests, no sound of insects in the night. The ocean may have been the main home of life, or at least the place where microbial life developed over long periods in environments rich in water, minerals, and energy. Ancient cells did not need light in the way plants today need light. Some may have lived on chemical energy, drawing strength from reactions between substances in the environment, near hot rock, near minerals, or in watery regions where conditions were stable enough for them to continue existing. Life at that time did not change the planet immediately, for a very long time. It may have been only a thin layer, a silent activity in water, in mud, on stone, in small chambers, and in environments the human eye, if it had been there, could easily have overlooked. But the power of life does not lie in noise. It lies in repetition. One cell divides, then another cell divides. A small community clings to a surface. A microbial layer holds sediment in place. A metabolic pathway is passed on. Across one day, that may change almost nothing. Across 1,000,000 years, it becomes a quiet geological force. Somewhere in that long flow of time, a new turning point appeared. Some organisms learned to draw energy from light. At first, photosynthesis may not have resembled the oxygen-producing form familiar in plants and algae today. But later, microorganisms such as the ancestors of cyanobacteria began to do something that would change Earth's history. They used sunlight, water, and carbon dioxide to create organic matter, while releasing oxygen as a byproduct for them. It may have been only a way of living. For the planet, it was the beginning of a very slow revolution. Picture an ancient, shallow sea beneath faint sunlight. On the surface of stone and sediment, thin microbial mats lie still beneath the water. They have no leaves, no stems, no forest green like the plants we see today. But they are doing something profound, capturing light and turning it into life. Tiny cells work to the rhythm of day and night. When the sun rises, they use energy. As time passes, they multiply, die, and leave layer upon layer behind. And in that process, molecule by molecule, oxygen is released into the water around them. At first, oxygen did not fill the sky. It did not immediately turn Earth into a breathable planet. Much of the newly produced oxygen may have reacted at once with iron and other substances in the oceans, becoming trapped in minerals, absorbed by the planet's surface, in ancient seas. Dissolved iron met oxygen and formed iron-rich minerals, settling down into layers of rock over time. Red and dark bands of sediment were laid down like slow records of a chemical transformation. Stone began to carry the color of oxygen long before the atmosphere became a world our lungs could endure. There is a strange beauty in that image. Tiny cells did not know they were staining the rocks. They did not know they were changing the oceans. They did not know that those small oxygen molecules, seemingly insignificant, would gradually accumulate across hundreds of millions of years and transform the entire surface of the planet. They simply lived in their own way. But when life does something for long enough, on a large enough scale, the small can become a planetary force. Then, at a very distant point in time, as Earth's chemical reservoirs gradually became filled, oxygen began to accumulate more in the atmosphere. This was not an event that took place in a single morning. It was not like a door suddenly flying open. It was a long, complex process, one that may have risen and fallen, paused, increased, and decreased, but eventually carried Earth into a new state. Later, humans would call it the Great Oxidation Event. The name sounds immense, but its essence began with organisms too small to see with the naked eye. A planet that once had almost no free oxygen in the air gradually entered a different age. For us, oxygen is life. Every breath depends on it. Blood carries it to the cells. The body uses it to release energy efficiently from food. But for many ancient organisms accustomed to living in environments without oxygen, oxygen could have been dangerous. It is highly reactive, capable of damaging fragile biochemical systems that were not prepared to resist it. And so, the oxygen revolution was not only a gift, it was also a crisis. Some forms of life had to retreat into places without oxygen, such as deep mud, rock, the bottoms of waters, or sealed environments. Other lineages gradually evolved ways to tolerate oxygen, and later, to harness its power. In that transition, Earth became a more difficult place for some organisms, but it also opened new possibilities for others. Oxygen allowed a more efficient kind of energy metabolism, and in the long run, that helped open the way for complex life. But we must remember that this path was very long. From oxygen-producing microbes to complex animals lay an immense stretch of time, not a sudden leap. The planet had to pass through many changes in its oceans, atmosphere, climate, geology, and cellular evolution before the world could give rise to larger, more multicellular, more diverse bodies. Even so, the seeds of the future were already present in those first changes. As oxygen accumulated, the ozone layer could later form high in the atmosphere, helping to reduce the dangerous portion of ultraviolet radiation from the sun, as energy was used more efficiently. Living systems gained more capacity to build complex structures. As the environment changed, life was forced to adapt, find refuge, develop protective mechanisms, and open new pathways. Nothing in that process was predetermined to create humans. Evolution does not write its script in advance, but every microbial change widened the map of the planet's possibilities. Imagine Earth as an enormous dark room. At first, life is only a small lamp at the bottom of the room, weak, almost not bright enough to see. But that lamp does not go out. It multiplies into many small points of light. Then some of those lights learn to draw energy from the sun. That biological light does not blaze like fire, but it changes the air, the water, and the stone. Gradually, the room is no longer the same. the walls change color. The air changes composition. Doors that were once closed begin to open. A world once suited only to simple life slowly becomes a place capable of holding more complex forms of life. What is astonishing is that for most of Earth's history, life remained mainly microbial. We often remember dinosaurs, ancient forests, whales, birds, flowers, and humans, because those are images easy to see, easy to love, and easy to tell stories about. But if we look at the full length of time, microbes are the oldest, most enduring, and most deeply influential residents. They did not merely live on the planet. They participated in making the planet as we know it. They affected the atmosphere. They contributed to the carbon, nitrogen, and sulfur cycles. They lived in soil, in water, in stone, inside the bodies of other organisms. They are the invisible foundation of the living world. Even today, after billions of years of evolution, we still live because of a microbial world. In soil, microorganisms help matter decompose and return to the cycle of life. In the ocean, tiny planktonic organisms produce a large portion of oxygen and play an important role in the food chain. In our bodies, countless microorganisms live with us, influencing digestion, immunity, and many other processes. So when we think about the first living organism, we should not see it only as a stage that has passed. The microbial origin of life still surrounds and supports us every day. From one fragile cell, the story gradually became the story of an entire planet. Not because one single cell did everything, but because the principle of life was passed on. Preserve information, use energy, create boundaries, adapt, and multiply. Each tiny generation added another change. Each lineage found a way to exist. Some disappeared. Some left descendants. Some changed the environment around them. And the new environment then selected life in another way. Earth and life were no longer two separate stories. They began to write each other. Stone was no longer only stone, because living beings could change its chemistry. Water was no longer only water, because within it there was metabolism, death, birth, decomposition, and renewal. The atmosphere was no longer only a lifeless layer of gas, because its composition carried the traces of tiny organisms that had lived across deep time. Even the colors of the planet gradually changed. From a world of dark stone, empty seas, and an unfamiliar sky, Earth moved toward a planet with living oceans, and later, green continents, clouds, oxygen, and intertwined cycles of climate and biology. Within that transition, there is no clear boundary where we can say, from here, Earth became a living planet. Perhaps it was alive as soon as the first cells became stable enough to continue. Perhaps it became more visibly alive when microorganisms began to spread and leave traces in stone. Perhaps it truly changed when oxygen began to accumulate and rewrite the chemistry of the atmosphere. But whichever point we choose, one thing is certain: life did not remain in one small corner. Once it had rooted itself in the planet, it began to spread into larger cycles, slowly but without stopping. Perhaps this is what makes the story of life's origin both humble and immense. Humble, because its beginning may have been only a small cell, a thin membrane, a fragile molecular system, a microbial community on stone. Immense, because from those things, The entire planet changed. No plan was needed. No will was needed. No organism needed to understand what it was doing. Life only needed to continue long enough, and by continuing, it transformed the world that had given birth to it. Look back at the path we have traveled, an earth that did not yet know how to breathe, lightning across the ancient sky, vents deep beneath the sea, molecules beginning to hold information, thin membranes creating an inside, a deep common ancestor no living thing remembers, faint traces in ancient rock, and finally, tiny microorganisms changing the oceans, the stones, and the sky. No part of that story stands alone. Each step is a threshold. Each threshold opens the possibility for the next. From chemistry to information, from information to boundary, from boundary to cell, from cell to a living planet. And now, as you take a slow breath, this no longer feels entirely distant. The oxygen in this breath is the result of a very long history. Your body, with every cell working quietly within it, still carries the ancient principles of life. The cell membrane still keeps the inside from dissolving into the outside. Genetic information is still being copied. Energy is still being transformed. The things that began in the ancient microbial world are still happening, silently, inside you. Perhaps that is the closest way for us to touch the first living organism, not by seeing it in stone, not by naming it precisely, not by reconstructing the full moment when life began, but by recognizing that we do not stand outside that story. We are a very late part of it. Every breath, every heartbeat, every cell maintaining itself inside the body is a distant echo of a time when matter first learned how to continue. Night falls over modern Earth. Somewhere, forests breathe in the darkness, waves strike the shore, microorganisms still live in soil, in water, at the bottom of the ocean, in places hot, cold, dark, and extreme. Cities glow with light, humans tell stories, children sleep peacefully, and the cells in every body still quietly perform their ancient work. Earth is no longer the empty planet of the beginning. It is a living planet, full of sounds, colors, and rhythms of breath. But beneath all that richness, the story still begins with fragility, a membrane, a molecule of information, a small cell, a microbial community no one could see. Those things were not large, but they endured, and sometimes, in the history of the universe, it is the most enduring things that can change everything. From one fragile cell, Earth became a living planet. And from that living planet, after billions of years, came a creature curious enough to turn back and listen to the story of its own beginning. And now, as our journey has passed through ancient oceans, deep sea vents, molecules that learn to preserve memory, primitive cellular membranes, and fragile traces in ancient stone, tonight's story slowly comes to a close. Perhaps the strangest thing is not that life has become so rich, with forests, oceans, animals, human beings, and eyes that can look up at the sky. The stranger thing is that all of it may have begun from something unimaginably small. Not a majestic creature, not a brilliant explosion, not a clear moment recorded in stone, but a chain of silent experiments carried out by nature. Chemistry collided with time. Minerals met water. Energy slipped through cracks in the rock. And somewhere, Among countless failures that left no trace behind, one tiny system continued itself. From that point on, every breath that came later carried a part of that history. Before us, before dinosaurs, before flowers bloomed, or the familiar sound of waves touched the shore, there were the first forms of life, so small they were almost invisible, yet enduring enough to open the entire story of a living planet. If you enjoy gentle, deep stories about Earth, history, mythology, and the ancient mysteries of the universe, follow the fan page so you will not miss the journeys to come. And if you are still awake, leave a comment and tell me where you are listening from, or what mystery you would like us to travel into tomorrow night. The origin of humankind, the extinction of the dinosaurs, or the places where life may still be hiding beyond Earth.